session of fluid mechanics. So today the second session is there, and in this session we will discuss the boundary layer theory, that means the problem related to the boundary layer, and also the problem related to the what say that, oh, one second, okay, no problem, just I keep the mute. Okay, so the problem related to your, one second, so problem related to your also there is a so we have a category related to the boundary layer, so in which we have to develop the boundary layer. Also very much focus about the Navier-Stokes equation. Why? Because in the past from past 2-3 years, the frequently 2 marks question related to the Navier-Stokes equation, they says that. So beta they supposed to be asked. Now we have know that the Navier-Stokes equation is nothing, it is a conservation of momentum equation. And the conservation of momentum with the, if you consider the momentum equation is what? Momentum equation is nothing, it is a force equation. So if you consider the force on a fluid element without the frictional effect, that means without the viscosity, that momentum equation, it is your Euler's equation. And if you consider the viscous effect of that fluid element, the momentum equation is your Navier-Stokes equation. So if you have a momentum equation, you can integrate it. So integral form of momentum equation is your Bernoulli equation, but mind it, integral equation of a Euler's equation is a Bernoulli equation. So integral Bernoulli equation is what? Bernoulli equation is nothing, it is an integral form of momentum equation. Why? Because Bernoulli equation will be applicable only in the viscid fluid. Okay, in viscid fluid, right? Okay, so let's start the today's lecture, today's sessions. So the first question is very important question, and this question is really very new question. Okay, yes. So this question is look like a little bit lengthy. Yes, it is a lengthy question, but this question is all about your concept of a Bernoulli equation, concept of a pressure distribution, all the things, a gradient, lift, drag, all the things of the single problem. Just you read the question. So first you have to look at this image. So this is your quotient hertz of a military base. So this is your military base, and it is a shape like a semicircular cylinder. So you have to design this, you want to design this semicircular cylinder of a military base. The designed wind speed, that means what is the wind it is. So you have to design according to your given parameter. What is the given parameter? The wind speed it is given. What is the wind speed it is given? Wind speed it is your wind speed it is your 330 meter per second, and the free stream pressure and density. So this is your free stream velocity, free stream pressure, and free stream density it is given. That means the air property it is given, okay, respectively. The quotient Hert may be considered to be a closed, that means no leakage, that means this is closed, no leakage is there, semi-cylindrical with a radius of 5 meter. So this is your Hert, okay, and this is a semicircular cylinder, okay, which is the length is perpendicular to the board and the radius is 5 meter, okay, which is mounted on the tie down blocks as shown in figure. So this are the blocks mounted on the blocks, okay. Now the flow in is such that the velocity distribution over the top of the Hert approximated by, so these are the given condition. So the radial velocity at a radius r is equal to 0. That means on the surface there is no radial velocity. There is no radial velocity, okay. Now, and this is u theta is your tangential velocity. That means what is the tangential velocity? This is given at a radius r. That means this velocity at the surface, this is also velocity of the surface, but velocity at the surface in the radial direction it is given, but the velocity at the surface in the tangential direction it is given -2 of free stream velocity into sine theta, okay. And the one thing is it is given you are not, you supposed to be not ignore the air under the hut. You not ignore this air under the hut. What they asking with this is very important. They says that what is the pressure distribution over the top of the surface of the quiescent hut. Okay, so we have to find what is your pressure distribution. Number second, what is the net lift? What is the net lift force acting on the quiescent hut due to the air? So what is the net lift is there. Don't forget to include the effect of the air under the hut. So there is a fluid flow is there, air is flowing. So some fluid is over the surface and some fluid is down from this surface. So you don't ignore this down fluid. Okay. What are the net drag force? Also you have to find the net drag force on the hut. Hint, a calculation may be not be necessary here, but some justification is required. You don't bother about the numerical calculation, that means putting the value, but the justification you must have to, you don't ignore. Okay, so this is the question for the today. Let's start the question. This is the design of the military base hut. Okay, we have to design this one. So first we have to design this one. So my dear, we have to take this figure, that means this is your line diagram of this hut. So we have to take this line diagram of this hut. So what is that? Quiescent hut is there. Quiescent hut. Okay, that means this quiescent hut, what is the shape? Half of the cylinder. Half of the cylinder. This is your half of the cylinder. This is a quiescent hut of half of the cylinder. Okay, and over the surface, that means this is your half of the cylinder. Let's suppose we have to draw it. So this is your cylindrical surface. Okay, and it is mounted on the base. Okay, mounted on the base. Okay, so this is your fix, this is your fix, and the radius it is given. Let's suppose this radius is r. Okay, and you have to measure any radius r which is angle theta. So this is the angle of measurement of this theta. So you have to measure the angle anti-clockwise direction. Okay, so this is your hut. Now what is that? So it is given the velocity at the velocity it is given, that means velocity at radial direction at r surface. This is a surface is equal to 0, and velocity in tangential direction at the surface is equal to, it is given minus 2 of free stream velocity into sin theta. This is given. Okay, this is what? This is your tangential velocity. This is what, beta? This is your tangential velocity. Okay, this is your tangential velocity. This is your tangential velocity. Okay, now my dear, so what first we have to define, this is your hut. Okay, okay, now, and there is a fluid flow. Now we have to apply, so first we have to find the pressure difference. First, as they says that what are the pressure distribution over the hut. So we have to find the pressure distribution. So to have the pressure distribution, we have to apply the Bernoulli equation. So let's suppose there is a point which is far from that hut. That means there is a, let's suppose there is an infinite point. Let's suppose this is a point infinite, and over the fluid is flowing. So fluid is coming and it will drag over it, and it will glide like that. Okay. Now there is a some fluid, say streamline, also it will go into it and it will drag. So these are the streams line. We have to select, these are the streams lines. Okay, These are the streamline. Okay, no problem at all. So this is the inside. So this point is what? Let's suppose the fluid is flowing inside. So this is outside, that means outside surface, and this is bottom. So let's suppose this is a top and this is bottom. So bottom fluid is trapped in that one. Why? Because there is no any chance to flow out. So this is your stagnation point. So this is your stagnation fluid. Stagnation. This is your stagnation. That means fluid is at rest under the base. Okay. Now we have to apply the Bernoulli equation at this point and on the surface first. So first, number A, Bernoulli equation. Let's suppose there is very less change in the potential head. There is a very less change in potential head. So we have to neglect the potential head at infinite to the surface. We have to neglect the change in potential head. So what is that? Pressure plus half of rho, the velocity, let's suppose v square at point infinite is equal to pressure plus half of rho v square at any surface, the top surface. You have to take top, any top point, any surface point. Okay. Hi Rahul, good evening beta. Okay, any top surface. Okay. Now put, what is the P infinite? P infinite, it is your P atmosphere, it is given. Okay. V infinite, it is given u infinite, and this is also given the velocity. How much the velocity it is given? 30 meter per second. 30 meter per second. Okay. And density of the air, it is given how much? 1.2 kg per meter cube. So we have to find the pressure at the top, yes, surface. This is not surface. This is surface, any point. Surface. That means at either is this point, this point, this point, this point, this point, this point, any point. So we have to find pressure at the surface. That means pressure at the surface. You have to find it. Okay. So there is a tangential velocity, it is given. In this question, the tangential velocity given, there is no any radial component. So there is no any radial component. So to take this is at a streamline. So any point the tangential velocity it is given u of theta at r. What is given beta? This is given u infinite. What this value it is given? It is given 2u. That means this is given minus of 2u infinite of sin theta. It is given minus of 2 infinite sin theta. It is given. So we have the surface, any point. This is any arbitrary surface. Okay, at this point. So put all this value. So we have to arrange like that. So here v of the surface is what? V at the surface square is what? 4 of u infinite square sin square theta. Put all this value. So here what is that? If you find P at the surface is what? P infinite plus half rho within bracket u infinite का whole square minus v of the surface का whole square. Yes or not? Yes or not? Now here we have to write P infinite plus half rho. You have to take u infinite. Why? Because v surface square is equal to 4 u infinite square sin square theta. So you have to take u infinite common square. So this is your 1 minus 4 sin square theta. Okay, 4 minus sin square theta. So from here we have to take the difference. That means PS surface at any point minus P of the pressure at far from that means atmospheric pressure divided by, you have to take half rho u infinite square. This is what beta? 1 minus 4 sine square theta. Yes or not? Now my dear, this is what? This is what? Change in pressure divided by the dynamic pressure. So these are the coefficient. That coefficient is pressure coefficient. This is your pressure coefficient. And the pressure coefficient, why? Because this is the dimensionless. This unit is dimensionless. So this is the change in pressure. This is your change in pressure, and this is your dynamic pressure. This is your dynamic pressure. 1 second. This is your dynamic pressure, okay? This is your dynamic pressure. Okay, this is your dynamic pressure. So this is called pressure coefficient C. This is your C of pressure coefficient at the surface, and this is called pressure coefficient. Pressure coefficient. Now we have to find the pressure distribution. To find the pressure distribution, this is the pressure coefficient. First we have to draw this pressure coefficient versus this theta. So if you draw the diagram, see my dear, if you draw the diagram, okay, so this is your diagram, and this is your pressure coefficient Cp, pressure coefficient versus theta. So my dear, what is this pressure coefficient? Cp of the surface is what? 1 minus 4 sine square theta. Now let theta is equal to 0. Let theta is equal to 0. Let theta is equal to 0. So at this point 0 degree. So at theta is 0 degree. Theta is 0. Cp is 1. Pressure coefficient is 1. Let's suppose this is the pressure coefficient at 1. Okay. So this is the pressure coefficient corresponding to 0. Now, if we take theta pi by 2, that means there are 3 conditions. Theta 0 degree, theta pi by 2, and theta is equal to pi. That means this is your front, yes or not? This is your back. Okay, this is your back. Theta 0 back. This is your top, and this is your front. See, this is your hut. So this is your theta 0 degree. Here theta 90 degree. Here theta 180 degree. Yes or not? This is your back, this is your top, and this is your front. Okay, so we have to, so what is this value? Theta is equal to 0, corresponding to pressure coefficient on the surface is equal to 1. If theta is equal to pi by 2, pressure coefficient on the surface, it is your pi by 2. Pi by 2 pe, it is your minus 3. Theta is equal to pi, again surface is equal to 1. Okay, again it is equal to, no, this is your at pi by 2. Pi by 2 it is 0. Yes, pi by 2 it is 0, and this is pi. that means this is a pi by 2 is minus 3. It is correct. This is your minus 3 and again pi it is your 1. So this is 1. Let's suppose this is your 0.1. Let's suppose this is your 0.1. Let's suppose this is your 0.1 and this is your point minus 3. This point is 1, this point is minus 3, okay, and this is your 0 at a 0. Theta is equal to 0, theta is equal to pi by 2, and theta is equal to pi. Okay, so if you draw minus 3, what minus 3? Minus 3, correct, minus 3, correct. So if you draw this line 0, so it is like that, pi by 2 minus 3, pi by 2 minus 3, again this is your 1, again this is your 1. So it is moving like that. That means the pressure distribution, it is like that. One second, beta. Take this color. Okay, this color. It is like that. One second. And this is like that. Yes. That means at this point. Okay, this is your pressure diagram. This is your pressure diagram. Clear? This is your pressure diagram. Now, my dear, if you see that at a theta, the pressure coefficient of pressure is maximum. At pi by 2, the coefficient of pressure is minimum. So, if you draw the pressure distribution, okay, if you draw the pressure distribution, so this is your pressure distribution. Now, if you find pressure under the hut, if you find the pressure under the hut, so take the another streamline. So this is a streamline where the velocity is u infinite, pressure is p infinite, and there is no any datum, and here is the velocity is 0. So you have to find the pressure under the head. Why? Because this is a stagnation point. Okay, this is your stagnation point. So the pressure we have to find. Next one. The pressure under hut be the stagnation pressure. Why? Because under the hut this pressure is higher, and under the hut this pressure is very, very minimum. So we can neglect the pressure at this point. Under the hut is stagnant pressure. So stagnant, no, not minimum. This is a pressure and there is a velocity, and here the pressure is maximum. Why? Because it is within this one. This is the maximum pressure, and the maximum pressure where the velocity is 0. Where the velocity is 0. So at this point the velocity is 0. Okay, this is one catch. So if you apply the Bernoulli equation, what is that? One second. If you apply the Bernoulli equation, okay, so P plus a half rho V square at far from the hut is equal to P plus half rho V square. This is your bottom. Okay, this bottom, that means this at the bottom the velocity is 0. Why? Because a stagnant point. A stagnation point. Okay, so this is 0. So what is the P of the bottom? That means P of the bottom is equal to free stream pressure plus half rho U infinite ka whole square. Okay. So here, what is that? PB minus P infinite divided by half rho U infinite is equal to coefficient of pressure of the bottom. So if we write like that, PB bottom pressure minus free stream pressure divided by half rho U infinite k square. So this is also coefficient. So this is Cp of bottom. And my dear, see this one, when this is possible? When this is possible? See, in this question, see this one, when this is 1, when this is 1, when theta is equal to 0 or theta is equal to 180. So theta is equal to 0 or theta is equal to 180, theta is equal to 0 or theta is equal to 180, this value is equal to 1. So if you divide this one, this is 1. Okay. So at 1, the pressure is maximum. At 1, the pressure is maximum. That means under the hut, the pressure is maximum. Why? Because this coefficient of the pressure gives the maximum value. Gives the maximum value. Okay. That means if you draw the diagram, that means if this is your hut, semicircular. So at the bottom, the pressure is uniform and it is maximum. And it is maximum. Why? Because this pressure and this pressure is maximum. And at the front, at a 0 degree, the pressure is also maximum of a same magnitude. Here the pressure is also maximum of the same magnitude, but here the pressure is very minimum. So if you draw the profile, it is look like that. It is look like that. Here the minimum pressure, here the minimum pressure, and the pressure will increase. Here the pressure will increase. Here the pressure will increase. That means at the top, the pressure is minimum. At the top, the pressure is minimum. At the top, the pressure is minimum, sin 0. Yes. That means at the top, the pressure is minimum. At the front and at the back and at the bottom, the pressure is maximum. Clear? This is clear up to this one? Is there any problem? Please tell me. So the top have a low pressure and bottom have a high pressure. So there must be a lift in the upward direction. There must be a lift in upward direction L. There must be a lift in upward direction. That means net lift in upward direction. Okay. So we have to find what is the lift. What is the lift? So it is clear, beta, everyone? Rahul, this is clear up to this one? Is there any problem? Please tell me. Is there any problem? Clear. Okay. So now the second thing. So the first thing is clear. How to draw the pressure distribution? What is the pressure distribution over the top of the quotient hut? So that is the pressure difference. Now the second one is what is the net lift force acting on the quiescent hut due to the air. So due to the air, what is the net lift? That means lift L you have to find it. This L value you have to find it. What is the L value? So if you find the lift, you have to consider, so net is upward. Net is upward. So and the top, that means the surface, this lift, the bottom is clear. There is no any problem. Why? Because the pressure is uniform and that is the maximum. But on the top, the pressure is varying. So we have to integrate the, that means if you integrate the total, so if you find the lift of, if you find the lower portion, net lift is there, na? So that means this one minus this one. So if you take this is positive, so if you take this is negative, so minus, so this is negative, so this is positive. So this upward minus net of downward. Net of downward. Why? Because if you take any component of this one, so this is your downward and this is your in this direction. And if you take this one, so this is your downward and this is in this direction. So the net horizontal is 0. Why? Because it is symmetrical. Net horizontal on the top it is 0. So net vertical downward it is there. So net vertical downward minus net vertical upward is the net, is the lift. But the net vertical upward it is uniform, so don't bother about that one. What is that? Pressure into area. Pressure or force upon area. So what is the force? Pressure into area. You have area and you have a pressure. So pressure into area is the upward direction. Now, but this pressure, you have area of this one, but the pressure is non-uniform distribution. Pressure is non-uniform distribution, so you have to take elemental part. That is the mathematical model. Why? Because pressure is non-uniform. Bottom it is okay. Bottom, all the point the pressure is same, but the top the pressure is non-uniform. So you have to take the elemental portion. So for that one, this is our hut. Let's suppose this is our hut. Okay. Okay. This is our center. Okay. We have to take this element. So this element, we have to take this element. This is your theta. So we have to take this elemental part. At this element, the pressure is uniform. You have to take this element. At this pressure is uniform. At this element, the pressure is uniform. And this angle subtended by the this point, let's suppose this is d theta. What the angle? D theta. So at this point the pressure it is, so what is the area of this one? dA. What is the area? This r, this radius r into r d theta is the length. Theta is equal to L by r. So what is the this arc length? L is equal to r d theta. It is your length into perpendicular to this one. That is your area. So this is your length into the length which is perpendicular to the board. Let's suppose this is a width B, it is given. The length it is given. Length of the hut it is given or not? Please see this. See the hut, okay? And then to design the hut, the radius itna we have to down tight. Okay, no problem. So per unit weight, per unit length in this direction, you have to take this direction. It is your width, and width it is per unit width. You have to calculate per unit width. Okay. So let's suppose this is your B. This B is the width of this hut. Okay. So this width of this hut. Okay. So so area it is there. So on this hut, on this top surface, this is your pressure acting in this direction. What is the force? This pressure force which is varying PS into this area dA, and these are the distributed over the surface. Okay, and this is your uniform velocity U infinite. And what is the lower force? The lower portion is what? This total is your 2R. This, so this total is your 2R into the width, it is your area. This is your area into pressure at bottom. Pressure at bottom. So, if you find the net lift, that means net lift. So, from this one you have to integrate, this is theta, this is theta. So, theta is equal to 0 to theta is equal to pi. You have to integrate it from the top one. So, this one is downward. So, let us suppose 0 to pi, okay, 0 to pi, and this is your downward. So, take negative. This let us suppose this is our positive direction. This is our positive direction. So, this is your downward. So, minus P of the top into. So, this is your horizontal component and this is your vertical component. So, in the lift, we have to only include the vertical component. So, vertical component is downward. So, this is angle theta. So, this is also theta. So, what is this component? This component is PS into dA sin theta, downward. It is your downward. So, minus PS into dA, PS sin theta, and what is the dA? dA is nothing, r d theta is arc length into width b. Clear? This is clear. Now, so integrate from 0 to pi plus bottom. Bottom is what? PB, and these are the uniform into 2r into b. This is clear? Everyone please tell me. So, this is what? This is your dA. This total is what? This is force on the top. And this is what? Bottom. This is clear, beta? Everyone please. This is clear? Everyone please tell me. This is clear or not? Rahul, this is clear, beta? This is clear? Everyone please tell me. Okay. So, now you have to solve it. Now you have to solve it. So, what is that? What is PS? You have a PS, you have a PB, yes or not? So, if you have a PS, what is the PS? This is your PS. This is your PS. You have PB. This is your PB. Put the value in this equation and integrate it. Put the value of this one and integrate it. So, L is equal to, take minus outside, 0 to pi. What is PS? P infinite plus 1 by 2 rho u infinite square, okay, into 1 minus 4 sin square theta. So, this is your PS into sin theta into r d theta into b. This is your okay. So, here you have to write, this is your PS. So, this is your PS. Clear? Now, plus PB. What is your PB? Plus PB is what? P infinite plus half of rho u infinite the whole square into 2r into b. So, this is your PB. So, this is your PB. Tell me, this is clear or not? This is clear? Please tell me, this is clear or not? This is clear or not? Please tell me. This is clear, beta? This is clear? Now the next task is very that means what we say that mathematics. So this L. So what is the lift coefficient? Lift coefficient is your lift divided by the dynamic force. So lift. So if you define the lift coefficient from here, what is the lift coefficient? This lift divided by pressure half dynamic U infinite square. So this is dynamic pressure into area. What is the area? 2R into B. This is your area. So this is your lift. So this lift divided by this force. So you convert, it is in the force. So if you convert, you multiply the area. So this is your coefficient of lift. So your lift is there, divide all the term. So this is L. So L, from this one you have to divide this portion. Okay. So CL, if you divide this one, this is your theta is equal to 0 to theta is equal to pi P infinite into R into B divided by half rho U infinite square into 2R into B plus 1 minus 4 sine square theta divided by 2 into sine theta d theta plus P infinite divided by half rho U infinite का whole square plus 1. Okay, if you divide all the term, that means if you divide this term into each and every term, so this is L, put this L here and divide this term. So this L you have to put here and this will divide. So this is your result. Okay. Now, so if you take half, so this is your minus. Don't ignore, this is your minus. Minus is there. Minus is already there. Minus is there. Okay. So take half. So this 2. So this 2 you have to take like that. This half you have to take like that. That means minus of 1 by 2 0 to pi into this 2 RB cancel. 2 is outside, so RB cancel. So P infinite by half of rho U infinite ka whole square. Okay. Plus if you take this one, so divided by 2. Okay, divided by 2. So this is your 2 is outside. So this is your 1 minus 4 sine square theta into sine theta d theta plus P infinite half rho U infinite ka whole square plus 1. Clear? Now, if you take this one, this is your this quantity. If you integrate sine theta, so this is constant term, put outside. That means minus of half P infinite 1 by half rho U infinite ka whole square outside sine theta d theta. That means integration 0 to pi sine theta d theta. Okay, minus, so and multiply. So this is separate term, this is separate. Now minus 1 by 2 minus 1 by 2 here sine theta integration 0 to pi sine theta minus 4 of sine sine q theta d theta. हाँ negative first term, okay, d theta plus p infinite divided by half rho u infinite k square plus 1. This is okay? Please tell me. This is okay, everyone? Please tell me. Up to this one, there is any problem? Please tell me. Up to this one, there is any problem? Please tell me. No problem. Okay. Now, what is this value? What is this integration? This is your minus cos theta 0 to pi. So, this is how much? This is how much? 1 plus 1. That means this is 2. So, this is value 2. Okay. Now, what is this one? So, here sin theta. So, this is your sin theta. Clear? Now, so what you have to write here? Here what you have to write 2. So, this 2 and 2 cancel. So, this term, total term, this total term is what? This total term is what? 2 cancel. So, this is your minus of p infinite divided by half rho u infinite k square. Yes or not? Yes or not? So, and minus of, you have remained this term. So, this is your minus of half 0 to pi here half. So, this is your half sin theta d theta minus minus plus into 2 0 to pi sin q theta d theta plus this term as it is. What to write? This is clear? So, again this value is 2. Again this value is 2. And now this value, if you calculate this one, so this value, this integration, it is your 4 by 3. This integration is 4 by 3. So, what is the equation now, right now? That means, see my dear, this is 2 into, this is 2 into 4 by 3, okay, 2 into 4 by 3 plus 1 is there, 2 into 4 by 3 plus 1 is there, and this is what? How much it is, beta? Please tell me what is this value? Please tell me. P infinite divided by half rho u infinite k square. Please tell me, Rahul, what is this value? What is this value? P infinite divided by half rho u infinite k square. What is this value, beta, Rahul? P infinite divided by half rho u infinite k square. What is this value? P infinite divided by half rho u infinite k square. What is this value? Please tell me. What is this value? This value is 1. See? See this one? P infinite, that means P infinite half, this is the value of 1. Okay? See this one? Here, if you write like that, back pressure, that means if you write here P infinite, that means the ratio. Here P infinite plus half rho u infinite k square is equal to 0. Is equal to 0. What is the condition here? Please tell me. P infinite plus half rho u infinite k square. Yes or not? And this is constant at this point. And why? Because the Bernoulli equation. So P right side, and if you write at this point, stagnation point. So at this point, rho infinite. So this is 0. So if you write like that, this is constant. What is this value? Please tell me. What is this value? Please tell me. P infinite plus 2. Okay, so this is 2. No problem. Yes. We have to take this one in the form of gauge. If you find in the form of gauge, if you find what is that in the form of gauge, if we find the form of gauge, so this one and this one is 0. So good evening Manish. So if you find, so we have to find the gauge 1 with respect to atmosphere we have to find. So gauge 1. So from the gauge 1, this value of P infinite tends to be 0, and from the gauge 1 this P infinite tends to be 0. So what is the value here? There is 1 plus 4 by 3 into 2 minus 1. Clear na? So this is what? Minus 1 by 2 into 2. Minus 1 is there. Plus 2 into 4 by 3 plus 1. Why? Because this we have to count in the form of gauge. So in the form of gauge, atmospheric condition is 0. So we have to find, that means in terms of gauge, so P atmospheric, which is P infinite, is equal to 0. So if we write, so what is the CL? CL, it is your, so this is 0, this is 0. So minus 1 by 2 into 2, minus 1 by 2 into 2 plus 2 into 4 by 3 plus 2 into 4 by 3 plus this is 0, so plus 1, plus 1. What is this value, beta? So this and this will cancel, so this is 8 by 3. This is CL, lift coefficient. This is your lift coefficient 8 by 3. This is your lift coefficient 8 by 3. This is your lift coefficient. Clear? Clear na? Clear beta? This is your lift coefficient. Now if you have lift coefficient 8 by 3, that means what is the lift? What is the lift? This is what beta? L divided by half rho u infinite ka square into area 2r into b width. So what is the lift here? The lift, it is equal to 8 by 3. That means lift 8 by 3 into half rho u infinite square into 2r into b. This is your net lift. This is your required net lift. Clear? Clear beta? 8 by 3. Correct. Clear? Clear this one? Clear? Everyone please? Yes. Yes. This is clear, lift? This is clear beta? Everyone please? Now tell me, now the second part is, so we have a pressure distribution, clear? So the second, so this one is, what is the pressure distribution over the top of the quotient hut? So we have a pressure distribution here, low pressure, high pressure, high pressure. What is the net lift force acting on the quotient air? This is clear. Now what is the net drag force acting on the hut? So what is the net drag force in this case? Please tell me. What is the net drag force? What is the net drag force beta? Please tell me. Net drag force. So this is your hut. This is your hut and this is your pressure distribution. One second. This is your pressure distribution. This is your pressure distribution. This is your pressure distribution. This is your pressure distribution, my dear. Okay. So we have to find the drag. So which is responsible to drag this horizontal component. Drag is a horizontal component, lift is a vertical component. So let's suppose there is this is your pressure. So this horizontal component and this vertical component, and this is your theta. So this horizontal component will produce the drag. So this horizontal, and if you take this is your pressure, so this horizontal component and this vertical component. So this vertical component include with the lift, and this horizontal component is your drag. And this horizontal component is symmetric about this axis. So what is the net horizontal component in the right side? The same is the net horizontal component in the, what is the net horizontal component towards the left side is the same as the net horizontal component towards the right side. Why? Because this is the symmetrical pressure distribution. So net drag is 0. So in this case the net drag is 0. So net drag force is your integral of horizontal component of pressure force, okay, horizontal component of the pressure force. And this horizontal component of the pressure force is symmetrical about center plane of cylinder, cylinder. So net is, if drag, net is 0. Clear? You can also find the value of this one, no problem. So what is the, this is the horizontal component. You can find easily. You can easily find of this one. How? You can easily find what is the net drag. So from the net drag you have to integrate from 0 to pi. You have to integrate from 0 to pi. So integration from, so net drag d is equal to 0 to pi. Now you have to integrate the component. This component is what, beta? P cos theta. Yes or not? This is your P cos theta. So P is the surface. That means, and this is your in this direction, let's suppose. You're starting from the 0 to pi. So this is your minus of P cos theta into the area. What is the area? R d theta into the B. If you solve this one and you have a PS surface, put this value PS, integrate it, the value it is 0. And the physically what you, why, how to understand that? Why? Because sir, in this symmetrical plane, this pressure is acting, so horizontal component in this direction is, and horizontal component of this direction is the same, so net drag is 0. So the military base will have to design only for the lift condition, okay? Clear? Everyone, it is clear, beta? It is clear, everyone? Please tell me. This is clear or not? Please tell me, beta. This is clear? Okay. Now, so further we have to go through the next problem. So before the next problem, we have a one announcement. What is that, beta? These have a IMS features. What is that? For the GATE 2025-26, we have a feature programs. What is that? We have a 800 plus hour live classes with a live interaction. That means the faculty will interact directly, and in the, it is in class, offline classes, not online classes. Theory book, exercise book, and 30 plus year GATE question bank with a video solution. That means we have a theory book, we have also exercise book, And theory book, it is all the theory book, there is all the concept note point is there. There is a exercise book in which level 1, level 2, level 3 is there, and 330 plus year the get question PYQ. And what is the uniqueness of this PYQ? There are two uniqueness. First is your video solution, that means there is a QR mark, and the second one is that you have an alternate solution also. Fourth one, this is the especially for the IMS features. What is that? We have to 3 1-to-1 personalized mentorship program. Okay, so you have to directly connect with the faculty, and you have to 1-to-1 session and 130 plus online test series. If you know more details, just you have to dial this number. Okay, now the next thing is, this is your important, very important thing, the Telegram group. So I request you all that you can join this Telegram group. There must be advantage. What is that advantage? Schedule of the free YouTube lecture. That means if you update the free YouTube lecture, the question is level, how the question, when the YouTube series will start. Why? Because some student says that, sir, what is the timing? So if you join this Telegram, there is update is there. Lecture of that PDF, that means what is the lecture today will delivered, all the PDF is there. Important updates related to the seminar and the webinar, if there is any seminar is going on, so there is updated. Also there is a notification of the government job. Expert session on the important topic, expert session we will take also, a date is there, and daily cues and many more. So you have a daily queue. So join with this Telegram group. Okay, thank you. Now the second question is this one. This is little bit simple question, but the frequently asked in the GATE exam. This type of question. So there is a pipe of a non-uniform cross section. This cross section, in this one, the pipe, there is a oil is there, and oil have a specific gravity 0.9, and that is the section 1. So you have to take, this is our section 1. This is our section 1. This is our section 1. Let's suppose this is our section 1. This is section 1. Okay, this is section 1, and this is section 2. There is a vertical pipe, and there is a streamline. So this is a streamline. So this is 1.1 and this is 0.2. Let's suppose here the pressure is P1 and here the pressure is P2, and we have to connect this a manometer, YouTube manometer. Why we have to connect? To find the pressure difference. Okay, so this is oil and there is a mercury is there. So first we have to find the pressure difference, that means P1 minus P2. We have to find P1 minus P2 pressure. What is the P1 minus P2 pressure? And also there is a mass flow rate through the pipe. Mass flow rate you have to find. So for the mass flow rate, you must have know about the discharge. Okay, so these are the question. And the dimension it is given, the section 1 diameter 300, section 2 diameter is 100. Height, this H height it is given, that means the distance between the section 1 and section 2, 600 meter, and this height H, that means manometric deflection it is given H value, and H value is 100 mm. Clear? Now we have to start this problem. So to start this problem, what is that? First apply the manometric concept equation, and to understand the pressure balance, that means you have to balance the pressure from the manometric equation, and you have to find the pressure difference. Then we have to apply the Bernoulli equation. From that Bernoulli equation, we have to apply the mass flow rate. So what we have to do, first determine the pressure difference by using the manometer. And then apply Bernoulli's equation along the streamline at point 1 and 2. That's it. These two methods you have to apply for this one. Okay, this is the gravity. Now, so for that one, Okay, just start. Okay, just start. Okay, so we have the two section, that means we are not bothered about to draw much more. This is your section like that, vertical section. Okay, there is a manometric fluid, there is a manometer connected to it, not like that. There is a manometer which is at this point. Okay, this is your manometer. Okay, this is point 1, this is point 1, and this is point 2. Okay, this is point 1 and this is point 2. Okay, now we have to find so what is that? P1, this horizontal pressure is same, so P1 pressure, so we add here, and this height it is given, this is your H height it is given, I think, this connection, this is your H height, H is it given, and here it is up to this one, there is a manometric fluid, here it is a manometric fluid, so this fluid height from this one, this is your a small h is given. Let's suppose this distance is x. Okay, now so we have to apply P1 plus, in this one there is up to this one there is a oil, so density of oil G into H height H plus a small x, H plus a small x, so this is up to this one there is a small x, and up to this one there is a small h. So at this point we have to find P1 plus this one. Why? Because we are moving along the gravity, so rho naught G capital H plus a small x plus a small h. So we are at here, now from here to here we have to jump it, so this is in the mercury, so plus, so at this point, so plus, and we are move upward, so there is a minus. From here you have to jump and move upward through height h, so minus of hg rho g into height small h. Now again you have to move in oil, this is your oil, so minus of rho of oil g into x, so you are at here, and this here pressure is same, that is equal to P2. Clear? This is clear? Now, so this x quantity and this rho g naught x quantity is cancel out, so don't bother about the x. So what is that? P2 is equal to P1 plus. Now we have to put it is in a specific gravity of equivalent to water. That means we know that a specific gravity of water is equal to density of oil, yeah, anything, density of any fluid divided by density of water. Okay, so density of fluid, that means you have to find the density of oil. So density of oil is your specific gravity. This is your specific gravity of any fluid. One second. A specific gravity of any fluid is equal to density of that fluid divided by density of that water. So a specific density of any fluid is equal to a specific gravity of oil into density of water into H capital H minus a small h minus of density of Hg. So density of Hg, specific gravity of Hg into density of water G into a small h this is equal to P2. So if you common something, that means this is your not PO, this is your P2. So this is clear, no problem. Okay. Okay. So what is that? P1 minus P2. P1 minus P2 is equal to density of water you have to take common. G you have to take common. So here G is also there. So G common into specific gravity of Hg into small h minus specific gravity of IL into capital H plus small. So this is clear? Everyone please tell me, this is clear? So this is a pressure difference. This is clear, beta? This is your pressure difference. This is clear? Everyone please? Now you have to put all this value, density of water you have, G you have, a specific gravity, all this value you have. See this one. All the value you have, specific gravity you have, specific gravity of Hg you have, Hg you have, D, all the things you have. So if you put this value here, the value it is your 7.2 kilopascal. This is a pressure difference. Once you have a pressure difference, just apply the Bernoulli's equation between the section 1 and section 2. So apply the Bernoulli's equation. Apply the Bernoulli's equation. What is the Bernoulli's equation? P by density of oil into G plus V square by 2 into G, 2 into G plus Z at point, let's suppose 2, is equal to P by rho naught into G plus V square upon 2 plus Z at point 1. You have to take, this is your reference datum. This is your Z. Okay. So this is your 2. So you have P2 minus P1. P2 minus P1. Sorry, this is your P1 minus P2. This is your P1 minus P2 now. What is there in the question they are asking? P1 minus P2. P1 minus P2. So this is your P1 minus P2 you have. P1 minus P2 you have. So if you write P1 minus P2, so what is this value here? From here, from above equation, you have P1 minus P2 and try to in SI unit in Pascal. So this is your 72 kilo 00 Pascal. What is V2 here? If you convert it in discharge, so V2 is equal to discharge by pi by 4 d2 square. What is V1? Discharge by pi by 4 d1 square. Okay, 7.2 kilopascal, correct. And Z1 minus Z2, Z1 minus Z2 is your H. Put all this value and rearrange like that. That means P2 minus P1 divided by rho naught into G minus H is equal to, put this value, 8Q square divided by pi square into G 1 by d1 पे power 4 minus 1 by d2 पे power 4. Now we know that mass flow rate is equal to density of oil into discharge, and density of oil and discharge from here you can arrange and put this one. So this is square root of pi square g divided by 8 into d1 पे power 4 minus d2 पे power 4 divided by d2 square minus d1 square into p2 minus p1 divided by rho naught into g minus 1. That's it. Put all this value, rho naught, pi, all these values you have. So mass flow rate is 37.5 kg per second. This is clear? This is clear, beta? Everyone, please. What you have to do, just rearrange, that means put this value, this discharge value V1, put this is your V2, put V2 here, put V1 here, P, and rearrange this one. From the rearranging, you have to this one, you have to find Q value here, put this Q value here, rearrange like that, put all the given value. What is the given value? It is given, beta. D1 it is given 300 mm, D2 it is given 100 mm, H it is given 600 mm, small h it is given 100 mm, and density of oil it is also given. You have to put like that 900 kg per meter cube. Okay, that's it. That's it. And P2 minus P1, you have pressure difference. Put all this value, find the answer. Clear? So these are very simple problem. These are the very simple problem. Now we have to start with the next problem. And that is your very important content part for the today. That is your conservation of linear momentum. So we know that the linear momentum equation, that means conservation of linear momentum equation, is nothing. It is a force equation. Hierarchy. Good evening, beta. It is a force equation, and the force equation is applied. That means if there is a element, fluid element is there, and the fluid element you have to assume that move with the viscous effect and without the viscous effect. If you analyze the force without the viscous effect, the equation of the momentum equation is called Euler's equation. And if you assume the fluid is moving with the viscous effect, that means with the viscous effect, what is the equation of the motion? That means a momentum equation is called Navier-Stokes equation. So the Navier-Stokes equation, that means if there is a fluid, so if there is a two type, if the fluid is at rest or fluid is moving, what is the difference? If the fluid is at rest, there is no shear force. Only the normal force is there, that is called pressure force. But if the fluid is moving, along with the pressure, there must be a shear forces there. So in that Navier-Stokes equation, we have to assume the force have a three. One is the body force and other is your surface force. Surface force have a two component. One is the pressure force, other is the viscous force. So what is the difference between pressure force and viscous force? Sir, viscous force and pressure force. So viscous force and pressure force both are applied by the fluid itself, but the body force is applied not by the fluid itself, it is applied by the field in which the fluid is present. Yes, Navier-Stokes. Okay, so we know that for the Navier-Stokes equation, you know this equation. Everyone, please, yes or not, please tell me. You know this thing or not? Please tell me, you know this thing or not? So this is the momentum equation. Here is one thing is missing. What is the missing here? Anyone can tell? In this equation, one term is missing. Please tell me. Rahul, Rocky, Manish, everyone, please tell me. In this equation, What is the missing here? Please tell me. I will ask some question related to this equation. So in this equation, what term is missing? Please tell me. Please tell me what term is missing. Please tell me, everyone. Please tell me, everyone, what term is missing in this equation? Please tell me. Reply. I want your reply, beta. First, read this equation. Weight. No, weight is there. Rahul, weight is there. Wrong. You are wrong. You are wrong. Weight is there. Weight is there. This is weight per unit volume. Next one. Rahul, your option is incorrect, and try to attempt the next one. Weight is there. Anyone please? Weight is wrong. Weight is there. Rho into G. Rho into G. This is weight per unit volume. So weight it is there. Anyone? Please tell me. That means, Rahul, you don't know the Navier-Stokes equation. That means you are not aware much more. You know that, but not much more aware. Anyone? Anyone? Please. Okay. Anyone please tell me which term is missing? Now, my dear, I think you are not comfortable with this equation. Now, my dear, what is the Newton's second law? Net force is equal to mass dV by dt. Yes or not? That means this is mass. That means you can tell there like that, mass flow rate into change in volume, velocity. This is the momentum, linear momentum equation. Now, my dear, what is the net force? That means if the fluid is flowing, what is this net force? Pressure force. Force due to the pressure, gravity force plus viscous force. Yes or not? So, my dear, here the gravity force is there, here the mu it is there, that means viscous force is there, but here the pressure force is missing. So, in this term, plus, this is your in x direction, so dou p by not plus, this is minus dou p by dou x minus dou p by dou y minus dou p by dou z. This term is missing. That means pressure force is missing here. This is your pressure force. Now, my dear, see, gravity force is positive. Now, the next question. Gravity force is positive. Viscous force have a plus sign, but the pressure force have a negative sign. Why? Yes, Rahul, pressure gradient. Why the pressure gradient is negative? Anyone please tell me? Gravity force have a positive value, positive plus gravity force. That means gravity force positive, pressure, viscous force positive, but the pressure force, it is a negative. Pressure gradient is negative. Why it is a negative? Anyone please tell me? Why the pressure component is negative? Anyone please tell me? Why? Because, my dear, fluid is always flow towards the lower pressure, so that it is a negative. That means x will increase, pressure will decrease. So these are the condition of favorable pressure gradient. So due to make the favorable pressure gradient, you have to put the minus sign. That means while applying the Bernoulli Navier-Stokes equation, we cannot assume any boundary layer separation. So if we neglect, how to neglect the boundary layer separation? We assume that the flow, yes, flow in the direction of largest chain. What is that? Flow in the direction of largest chain. What is the flow in the direction? Okay, no pressure. So in the Navier-Stokes equation, we are not assume that the flow separation. So to nullify the flow separation, we have to assume that the fluid flow in the favorable pressure gradient. So what is the favorable pressure gradient? Pressure gradient, that means dou p by dou x is less than 0. Dou p by dou x is less than 0. That means if the pressure, if the distance will, that means flow distance will increase, the pressure is continuously decreasing. That means flow towards the decreasing pressure field. So it is negative. Clear? Clear? Now my dear, this is what term? This is what? Rho dou u x by dou t ux. So ux is the velocity in x direction. Uy is the velocity in y direction. Uz is the velocity in z direction. That means the velocity u is your uxi, uyj, uzk. Clear? This is the velocity field. Okay. Now, so this velocity field, this is the velocity with respect to time in x direction, and this is your, if you multiply with the density, so this is what beta? Acceleration. This is your acceleration with respect to time, and this is your acceleration with respect to position. If you multiply with the density, that is your force, which is per unit volume. Why? Because what is the density? What is the density? Density mass by volume. Density is what? Density is what beta? Density is what? Mass by. Density is what? Mass by volume. So mass into the acceleration, it is your force. Mass into the acceleration, it is the force. So force per unit volume. This is also force per unit volume. So this is your net force, and this net force in x direction is equal to is equal to body force in x direction, viscous force in x direction, pressure force in x direction. Net force in a y direction is equal to gravity force in y direction, viscous force in y direction, and pressure force in y direction. Net force in z direction is equal to gravity force in the z direction, viscous force in the z direction, and the pressure force in the z direction. Hi Sita, how are you? You are late again. How are you Sita? You are late again in the class, okay? But don't worry, I will explain you, no problem. So this is your density, density mass by volume, okay? Mass by volume, and mass into acceleration is the force. That means this term, all the term, this Navier-Stokes equation, all the term is divided by the volume. That means this is the equation force per unit volume. Everyone, please tell me. Anyone ask you, sir, this equation is the force equation per unit mass, per unit volume, or per unit weight. So this is your equation which is per unit volume basis. So generally the Navier-Stokes equation we have to apply per unit volume basis. Per unit volume. Why? Because see my dear, pressure, the unit is pressure is what? What is the unit of the pressure? Newton per meter square. What is the pressure? Newton per meter square. And this is your meter. So Newton per meter cube. Meter cube, that means volume. So per unit volume basis. So this equation, it is your per unit volume basis. Okay. Now my dear, so these are the Navier-Stokes equation. How to write the Navier-Stokes equation? Density into acceleration is equal to gravity force plus viscous force plus pressure force. Yes. Yes. So viscous force if you write, so viscous force if you write, multiply with the, this is your Laplace operator, del square. This is del square of ux. This is del square of ux, del square of uy, del square of uz. Okay na? So this is your mu in x direction, dou square ux, dou square ux divided by dou x square, dou y square, dou z square. Dou square uy, dou square uy, dou square uy divided by dou x square, dou y square, dou z square. Into in z direction, dou square uz, dou square uz, dou square uz divided by dou x square, dou y square, dou z square. This is clear. But in this one, if you write the acceleration in x direction, dou square x by dou t, that means velocity with respect to time, in x direction velocity, with respect to position, y x, that means u x u y u z divided by u dou u, thank you Sita, thank you very much, dou u x by dou x plus dou u x by dou y. So mind it, sometimes student get confused कि sir dou square u x by dou x square plus dou square u x या dou square u y या dou square u z, like that. So viscous term is the very clear, that is your dissipation. Why the viscous term is here? Why? Because that is creates a dissipation effect while the fluid flowing. Okay, so dou square, so this x is fixed, x direction velocity divided by that velocity in that direction, perpendicular direction. That means the velocity in x direction and that velocity the effect in y direction, in z direction, in x direction. That's it. The velocity in y direction, the y direction velocity have effect in x direction, y direction, z direction. That's it. Double differentiation. The velocity in z direction velocity in z direction effect, y direction effect, x direction effect. That's it. That is your viscous effect. But if you write the velocity in the temporal, this is your temporal with respect to time, and this is the position. That means what is the difference between the fluid mechanics and solid mechanics? In the fluid mechanics, we have to take the acceleration as the total material derivative. That means your Lagrangian approach, Eulerian approach. What is the Eulerian approach? That means you have to take a control volume analysis, but not a particle approach. So this equation, it is your Lagrangian approach, Eulerian approach. Why? Because Eulerian approach, the total derivative is the sum of the temporal plus local. But if you write the particle approach in the fluid mechanics, classical mechanics, when we prepare the IITs exam, where the acceleration is only dv by dt, that is your Lagrangian approach. Lagrangian approach with respect to time, yesterday class. Remember, Lagrangian is with respect to time only, but if you talk about the Eulerian, that Eulerian is the material derivative, that means a total derivative. The total derivative, it is the sum of the temporal plus convective. Clear? So, so let's suppose we have to take, now my dear, the very important information is that, let's suppose we have to take any direction, let's suppose x direction momentum equation with the viscous effect. So if you take x direction, take x direction momentum equation, what is the x direction momentum equation? Please tell me, with the viscous effect, please tell me everyone, please. What is that? Yes. So my dear, first is the how to remember? Net force is equal to mass into acceleration. This is in the form of vector. What is the mass? Density into volume. Density of mass by density is equal to mass by volume. So density. Okay. This is your acceleration. So this is your density into this acceleration per unit volume. Clear? So this is density and you have acceleration. Now, so first write rho. We have to write in x direction. So first is the steady term in x direction. That means partially dou u x by dou t. So this is your unsteady term plus velocity in x direction dou u x by dou x plus velocity in y direction dou u x by dou y plus velocity in z direction dou u x by dou z. That's it. So this is your acceleration is equal to gravity effect. That means per unit volume rho into g x direction. This is your x direction plus this is your body force plus viscous force. So viscous force multiply with the mu into that a gradient. That means x direction dou u x square by dou x square plus dou u x square by dou y square plus dou u x square plus dou z square minus dou p by dou x. It is clear, everyone? Please tell me. This is clear? Everyone, please tell me. This is clear? So this is your Navier-Stokes equation in x direction. Now, my dear, we have to reduce this equation very concisely. So in this equation, if you apply this equation, there is a one catch here. What is that catch? Is that, see my dear, what is the known here? Known. How many known is there? How many known is there? Density. You have a fluid, so you have a property known. Viscosity known, and gravity you know. That means you have three known value. You have three known value. Unknown, you have a velocity, and also you have don't know a pressure. That means what is the velocity? Velocity in x direction, velocity in y direction, velocity in z direction. That means how many unknown? 4. My dear, my dear, 3 known and 4 unknown. You cannot solve only Navier-Stokes equation. You cannot solve any problem. You have required one more equation. Why? Because known value is less, unknown is high. So if unknown is 4 and known is 4, you can easily solve. But if unknown is less, unknown is less, unknown is high, you cannot solve. So we have to find extra one equation. Which one equation is that? Please tell me. So there are 3 known and 4 unknown. We cannot solve separately this Navier-Stokes equation. So we have to another equation known as continuity equation. Continuity equation, and continuity equation is what? Conservation of mass equation. And what is the continuity equation, beta? Velocity in x direction divided by dx plus velocity in y direction divided by dy plus velocity in z direction, velocity in z direction divided by dz is equal to 0. So there are, that means now we have a known value. Now we have a known value. Thank you. Now we have a known, thank you Siddha. We have a known value. That means now we have a 4 known, 4. So we have a 4 known value. That means we have a 3 equation only. X direction Navier-Stokes equation, y direction Navier-Stokes equation, and z direction equation. So 3 equation is there. Now but 3 equation, and what unknown is there? 4. So we have to require one more equation known as continuity equation. So momentum equation, Navier-Stokes equation in x direction, 1 equation. Navier-Stokes equation in y direction, 2nd equation. Navier-Stokes equation in z direction, 3rd equation. But the unknown is 4. So 1 is the continuity equation, that means 4th equation. You can solve all the parameter. Clear? Now, how to write this equation in the form of vector? In the form of vector. So my dear, so in the form of vector, if you write like that, see this one, in the form of vector, you have to write like that. Vector form. Vector form. Now, so what is this one? Dou ux dou t plus ux, this is what? Total derivative. This is what? total derivative, also called material derivative. That means capital dv vector by dt. So the combined equation, this combined equation beta, this one, this combined equation we have to write in this side, we have to write du vector by dt into rho. This is very short form, and this capital D is the total derivative, or also called the material derivative, is equal to this dou by dou x, dou p by dou y, dou p by dou z. This is equal to minus of delta dou of p. This is the grade of p, gradient of p. Grade. So what is the grade? We know that grade is your dou by dou x, dou by dou y, dou by dou z, I, j, k. So this is your grade of p, del of p. Now, what is that? Plus. What is that? Viscous. Mu. What is that? Del square. Del square of u vector. Plus body force. That means rho into g vector. G vector matlab g in x direction, g in y direction, g in z direction. So this is your precisely vector form of Navier-Stokes equation. That means if you write vector form, rho du vector by dt is equal to minus del of p plus mu del square of u vector plus rho of g vector. Okay. What is this one? If you divide density all the term, so dou u vector by dou t is equal to, first write z vector plus mu by rho del square u vector minus 1 by rho del of p. Okay. Now, what is this one? How to write this one? This is the total derivative. Thank you. This is the total derivative. What is the total? Thank you, Sita. Thank you. This is the total derivative. What is the total derivative? Derivative with respect to time, del by del t plus temporal term, that means u vector dot del into u vector. So this is your total derivative is equal to, you have to split this one. This is very important. How to write the total derivative into the partial derivative. This is very important, I am telling you. 90% student get confused here. So first term is your temporal, second is your local. Okay. Second is your local. And as it is this one, so this is your g vector plus mu by rho del square u vector minus 1 by rho del of p vector. This is your precisely more generic form of the Navier-Stokes equation. So this is your temporal acceleration, this is your local acceleration, this is your gravity force, this is your gravity force, this is the viscous term, and this is the pressure gradient term. Okay. If the flow generally beta 99% the flow is steady. If the flow is steady like that, if you write like that, so this is your main equation. Now if the flow is steady, that means this density, it is there, na beta? Density, don't forget, density is also there. So here is the density, so multiply with the density, don't forget about. So for the for steady, this term is 0. This term is 0. So what is the left here? Rho dou u vector del u vector. So if the flow is steady flow, if the flow is steady, don't directly this take 0. 90% student take this is 0. This is a total derivative. This is a total derivative. Don't take this derivative. Partial derivative is 0. So this is 0. So for this one 0. Why? Because you have to take steady. Steady. So what is that? Rho into u vector dot del into u vector. Okay, this is your left side is equal to z vector plus mu by rho del square u vector minus 1 by rho del of p. Clear? Now my dear, sometime they says that there is inviscid, fluid is inviscid, that means inviscid fluid, that means the viscous effect are neglected. So this also will neglect. Okay, so this also will neglect, and they says that there is no any gravity force generally. So this is also 0. So what is the equation now? Inviscid. So rho, you can write like that, rho u vector dot del u vector is equal to minus of, so rho it is divided. Oh, here is not, rho it is divided, so don't put here rho. Okay, why? Because rho it is divided, so don't put here rho. Why? Because already divided, na? This rho is already divided, so don't put the rho. The rho is divided now, so don't put the rho. Okay, so rho is not here. Okay, already divided. So u delta v minus 1 by rho grade of p. So this is what, beta? Generally rho u vector dot del into u vector is equal to minus grade of p. So this is your continuity question. Generally the GATE question asked in this form only. So how to reduce the form, that is a very important thing. So this GATE question is asking. Now my dear, how to write this equation? This equation? Let's suppose there are two-dimensional flow. So now this is my Navier-Stokes equation. So what is the assumption of this equation? That means we have this equation, rho u vector dot del into u vector is equal to minus grade of p. So this is your Navier-Stokes equation, and this equation, what is the assumption of this equation? Please tell me, everyone, what is the assumption? Assumptions number first is steady flow. What is the assumption number second? What is the assumptions number 7? Inviscid flow. What is the assumption number third? Neglect body force. That's it. So these are the assumptions of this equation. Now my dear, if you write this in x direction, what is the x direction equation then? Rho. What is del x direction? So what is u? U vector is what? U x I, u y j, u z. Okay, this is u vector. Okay, Now, so this is u dot del. What is the del? Del is equal to I dou by dou x, j dou by dou y, k dou by dou t. This is a gradient, dou by dou y, dou by dou t. Sorry, dou by dou z, dou by dou z. So here is something is there, dot dot. Okay. Now multiply with this one. So this is your ux, x direction, into dou ux by dou x plus uy dou ux by dou y plus uz dou ux by dou z. Clear? You have to split it, is equal to x direction minus dou p by dou x. Let's suppose the fluid is 2 dimension. Let's suppose fluid is 2 dimension, yeah, planar flow. So if du, if any component of the velocity with respect to z differentiation is 0, that means if dou by dou z of the velocity component is equal to 0, that is called planar flow. Planar flow, and generally the planar flow is 2 dimensional. 2 dimensional. So for this one, this is 0. So for 2 dimension, what is the equation then? Rho ux dou ux by dou x plus uy dou ux by dou y is equal to minus dou p by dou x. Now my dear, this is your equation. Now if there is a velocity field, it is given. Let's suppose there is a velocity field given, u vector is equal to 3x y I plus 6 x j. Like that velocity field it is given. Like that velocity field given. So this is your ux, this is your uy. Clear? Put the value here, ux, differentiate ux with x, uy is there, differentiate with this one, multiply with rho. So there is a pressure gradient dou p by dou x, dou p by dou x. So you have a dou p by 2. Similarly, you have to find dou p by dou y also. So once you have to find dou p by, so you have dou p by dou x, you have dou p by dou y. Let's suppose something I vector, let's suppose something j vector. So if you add this two one, that means dou p by dou x plus dou p by dou y is equal to, let's suppose this is your xi and this is yj. So x plus y, yes or not, x plus y, this is your x plus y delta mein. So what is that means what is the grade of total pressure is equal to x plus y. This is the pressure field. So sometime you have to find the pressure field also with the help of Navier-Stokes equation. Clear? You have with the help of, that means this is your nothing, this is like that, xi plus yj, like that. So this is your pressure field and this is what? Grade. So grade, so this is not like that. So this is what? Grade of P, that means grade of P is equal to xi plus yj. You can easily find the pressure field. So if you know the analysis of Navier-Stokes equation, you can easily find anything. Clear? Now my dear, we have to use this equation of the Navier-Stokes equation for this something about the, we have to apply this equation. Okay, we have to apply this equation with the real problem. Before that, there is a, before applying the Navier-Stokes equation, we have a some assumptions, very important, and that is a very useful Why? Because while you are solving this differential equation, beta, you must have a the boundary condition. So for the applying the boundary condition, or which term is let's suppose which term is neglected, which term is considerable, for that one we have a special table. Always understand, always remember for that table. And also, my dear, I humbly request that please understand that table. That is your very important thing. No other platform can discuss these things. I am telling you. Start with that one. Okay. So my dear, assumptions. So there is your assumption slide. Assumptions. Okay. Very important, telling what is the assumption while applying the Navier-Stokes equation and continuation. Inward. In mathematics. So we have to make a table now, no problem. 1 second, 1 second, 1 second. We have to make a table, and that table is very helpful to you. Make a table. Okay. We have made a table. Now okay. Yes, that is okay. Now okay, no problem. First write down, no problem. Okay, so first one is inward. In mathematics. And this is your comment. Okay. Okay, please understand very carefully. Pahla, number first. Okay, number first. Number first, steady flow. So if there is a steady flow, what is that mathematics? Dou by dou t of the velocity, any component of the velocity is 0. Okay, that means nothing varies with time. Okay, this is the first comment. The second one, what is the second comment? Let's suppose you have to take it is in the box. It is in the box. So this is steady flow. This is for the steady flow. Okay. Now the second one is planar flow. Planar flow. What is mean by the planar flow? What is mean by the planar flow? Generally, in the case of planar flow, we have to assume the velocity in z direction is constant, and that constant sometimes it is 0. That means planar flow, and generally in the z direction, in the z direction, and z direction is nothing, it is a perpendicular to that. Means there is a plate, parallel plate is there, and the parallel plate, let's suppose this is x flow is flowing in this direction, so this is x direction, this is y direction, so the z direction we have to assume there is a no variation in the velocity in the z direction, either ux, uy or uz. That means velocity of x component in a z direction is 0, velocity of y component in a z direction is 0, velocity in z direction in the z direction is 0 with respect to that one. Okay, that means we have to take dou by dou z of any component of the velocity is 0, and if you write z, that means uz, that means dou z by dou z, dou uz by dou z is equal to constant. No change in velocity in that direction. Okay, Z. Other thing is 0. Now, that means what the comment is that there is no variation in the z direction, and velocity component is at most a constant in that direction. That is your planar flow. Now, the second one, third one is axisymmetry. You can say that fully developed flow in the dot direction. Let's suppose any direction. So fully developed, that means what is mean by the fully developed? Anyone place? What is mean by the fully developed? The flow is fully developed. What is mean by the fully developed? Everyone, please. What is mean by the fully developed? Please tell me. What is mean by the fully developed? That means the flow component, that means velocity in that direction doesn't change. So it is like that. Let's suppose velocity ux in that direction. Let's suppose any direction. Velocity uy in that direction is equal to velocity uz in that direction is 0. That means velocity doesn't change. Let's suppose example, let's suppose we have a x direction. Example. That means we have to say that fully developed flow in x direction. Let's suppose there is saying that fully developed flow in x direction. That means if there is a x, if you divide with respect to x, that means velocity component in x x component of velocity in x direction, y component in the velocity in x direction, z component of velocity in x direction doesn't change. That means there is no any change of any component of velocity in that direction. That means flow profile, that means a velocity profile doesn't change in x direction. So the velocity profile dou u by dou x, dou u x by, that means velocity in x direction, this is a velocity profile, this is the velocity profile, this is the velocity profile, but in that direction doesn't change. That is known as fully developed. That means the velocity component at the velocity component doesn't change in the dot direction. That means velocity component, any component of the velocity in that direction, let's suppose x, doesn't change in that direction. That is known as fully developed flow. Now these are the three assumptions and two are the condition. What is that? So there is some conditions. What is the condition? There are two conditions which is very important. I know that. That means conditions. So there is a conditions is there. What is the condition? Let's see. There are two conditions. Very important. There are two conditions. First one, this is a condition. Okay. So first one is no slip boundary condition. So this is also in the word. Let's suppose we have to write like that. This is also in the form of table. Okay. Now, so in word, okay, in mathematics, comment. Okay, what is that? No slip boundary condition. First one is no slip boundary condition. No slip boundary. What is mean by the no slip boundary? That means fluid velocity. What is the fluid velocity is same as the boundary velocity. Boundary. That means what is the velocity of the boundary is the same as the fluid velocity. That means if the boundary is rest, fluid is rest. If the boundary is moving, the velocity is fluid boundary velocity. That means it is like that, beta. What is that? This is very important thing. Let's suppose here, you have to write here. Oh, don't worry about that. You have to write like that. Let's suppose this is a two plates. Okay, now these are two plates. Let's suppose this plate is moving with the velocity u, and this is at a rest. This is at a rest. Now let's suppose there is any imaginary line. This is the boundary. This is, let's suppose this is a fluid A. fluid A, and let's suppose this is fluid B. Okay, fluid B, fluid B, fluid B. What is the boundary condition here? Let's suppose this boundary is moving with the velocity of v. So what is that means this fluid B at this point is 0. This fluid A at this point is the velocity of u. What is the velocity at this point? That means this fluid A and the fluid B have a same velocity of v. That means this boundary condition, it is not satisfied on a solid boundary, it is also satisfied on the fluid boundary. That means this is your fluid boundary. That means this is imaginary fluid layer which is moving with the velocity v. So at this layer, the fluid A and the fluid B have a same velocity. But at this layer, fluid B have a 0 velocity, and at this layer boundary, the fluid A have a u velocity. Clear? So you can say that in this sense, you can say that, sir, this line velocity at this point, this is your velocity, this is the fluid velocity A, this is the velocity 0, and that velocity, that means at this line, the fluid A velocity is the same as the fluid B velocity. This is clear or not? Please tell me. This is clear or not? This is very important thing I am telling you. That is the condition of no slip boundary condition. Is this clear? Rahul, it is clear, beta. Isita, it is clear. Everyone, please tell me. Manish, everyone. Manish, Rahul, Rocky, everyone, please tell me. This is clear or not? This is clear or not? Please tell me. So the fluid, what is the fluid velocity is the same as the boundary velocity. So this boundary either solid or either liquid. This boundary either solid or liquid boundary. So if this is your boundary of the liquid, so at this boundary, the fluid velocity are same. That means velocity of A is the same as the velocity of B, and what is that velocity? V. But at the solid boundary, it is rest, the velocity of the particle B is 0, and this boundary, the velocity of the particle A is u. Okay. Now, next one is, so what is the comment here? We have to do that. Okay, no problem. Just it is clear. Now, second one is continuous stresses at a boundary. What does they mean by this one? These are the terminology of fluid mechanics. That means, so there are two stresses. One is the normal stresses and other is the shear stresses. So normal stresses on the fluid is the same as the normal stresses at the boundary. Or second one, shear stress on the fluid is the same as the shear stress on the boundary. To understand this one, please see this one. Let's suppose this is your fluid flow and this is your at rest. Okay. Let's suppose this is your velocity u. Okay. Now, let's suppose this is your free surface. Let's suppose this is your free surface. That means this is your u. Let's suppose this is your free surface. This is your free surface. One thing. Okay, 1 second. We have to discuss this one. Okay, first we have to discuss this one. So here, the fluid, that means you have to take any layer. If you take any layer, though this above that one there is a different velocity, below that one there is a different velocity. Below this one, but at this edge of the boundary, this boundary have a same velocity. That means if you take, that means this is, let's suppose this is fluid A and this is a fluid B. So at the shear stress on the fluid is the same as the boundary. That means what is the, this is the fluid A and this is the fluid B. Let's suppose at this one. Let's suppose like that. Let's suppose this is fluid A and this is fluid B. So what is the shear stress? What is the shear stress by the fluid A on this boundary is the same as the shear stress by the B on this boundary. That means at this boundary, the shear stress developed by the fluid A is the same as the shear stress developed by the B at this boundary. Okay, that means tau A is equal to tau B at this point, at this boundary. Now, how is this defined? Let's suppose there are a free surface. At this free surface, let's suppose this at this point, what is the pressure? P atmospheric. So below that one, that means at this fluid, just below that one, there is a same pressure. That means this is also P atmospheric. This is also P atmospheric. So at this is a fluid boundary. So fluid boundary just above and just below, the pressure is same. Normal stress is same. Like that, the shear stress, if you take any boundary between the two fluid, that means this fluid is separated by this and this fluid is separated by this line. So at this edge, though there is a different fluid, but at the boundary, the shear stress developed by the fluid A on this boundary is the same as the shear stress developed by the fluid B on that boundary. Clear? This is clear? Everyone please, this is clear, beta? If this is clear, then we have to try to solve this Navier-Stokes equation. So these are the two boundary conditions. I am telling you, never see this. Please, you have to very much aware for this one. Otherwise, there is a very mistake is there. Okay. So these are the steady flow, planar flow, fully developed flow, no slip boundary condition, continuous stresses at the boundary. This is very important terms regarding the fluid mechanics. Okay. Now, we have to solve this problem. This is really very good problem. Please read this question carefully. What is the question, beta? Please read this question carefully. Please read this question carefully. Okay, I will read this question. A wide flat belt, okay, moves vertically upward with a constant speed u. This is your belt which is moving upward with a constant speed u through a large bath of viscous liquid as shown in figure. So there is a large bath. So this is your tank is there. In that tank there is a fluid is there, and you have to dip a belt, and then the belt you have to drawn it. While you have to drawn it, the some fluid will also be drawn by the belt. Okay. So shown in figure, the belt carry with a layer of liquid at a constant thickness h. That means while you have to drawn this belt, the belt carry some h thickness of the fluid also. The motion is steady and fully developed after a small distance above the liquid level. That means above the liquid level, the fluid is fully developed and steady. The external pressure atmospheric is constant everywhere, and this side the pressure is constant. Okay. Verify the governing equation to a form applicable for this practical problem. That means you have to verify the Navier-Stokes equation. State the appropriate boundary condition. Also you have to define the appropriate boundary condition. Determine the velocity profile in the liquid. You have to define the velocity profile. Determine the volume flow rate per unit depth. Depth is the perpendicular to the board. This is very good question, I am telling you. See my dear, what the question is say that there is a tub, bathtub, yes or no? this is your bathtub. Okay, this is your bathtub. In this one there is a fluid is there. Now there is a belt. Okay, this belt. If you drawn this belt, let's suppose if you drawn this belt will carry some liquid like that. It is like that. While drawing the fluid, it is like that. That means this H thickness of this liquid will drawn with respect to the, that means if you draw, let's suppose this is your belt, let's suppose this is your belt. Now if and dip it is in the liquid. Now if you draw it, due to the viscous effect, the along the belt some thickness of the fluid is also drawn. So this atmospheric pressure, this is atmospheric, all are the atmospheric pressure, and these are the belt, and these are the what line? This is the, this is what? Free, this is what? Free surface. This is also free surface. These all are the free surface. Okay, why? Because all the point the pressure is same. The pressure is same. Okay, so we have to design this problem. Very good problem. Very good problem. So this is your belt, beta. You have to try to solve this problem. This is your belt. So this is your belt. Okay, this is your belt, and this belt you have to draw with the velocity u. This belt is drawn with a velocity u. Okay, and this belt, let's suppose this belt dipped in a fluid. This belt dipped in a fluid. This belt dipped in a fluid. Let's suppose this belt dipped in a fluid. This is a fluid dipped. Let's suppose this is a fluid. One side. This is one side. So don't draw this side. Okay, initially this is your fluid. Okay, now this is your free surface. This is your free surface. Now if you drawn it, some layer of the fluid, which is the thickness of H, will also drawn along with the belt. So some layer of the fluid, let's suppose this layer of the fluid is also drawn. This layer of the fluid is also drawn. That means this layer of the fluid is also drawn. This layer of the fluid, let's suppose, no problem. This layer of the fluid is also drawn. This layer of the fluid is also drawn. Let's suppose. Okay, this layer of the fluid is drawn with respect to the plate. So this is your solid plate. This is your solid plate. This is your solid plate. And this is a fluid. This is your fluid. This is your fluid which is drawn. So this is your fluid, and this fluid thickness is H, which is drawn. Okay, this is your atmospheric condition. Okay, let's suppose we have to put the coordinate, to fix the coordinate. Let's suppose this is your x direction and this is your y direction. This is your coordinate. Let's suppose this is your x direction and this is your y direction. Okay, so x is equal to 0, we have on the planes belt, and x is equal to h, we have the edge of that free surface. Okay, this is your free surface also. Okay, now this is your belt and this is the direction of g. Okay, now clear, this is your liquid. Okay, let's suppose this is your liquid. Now what is that? First assumptions, we have to take assumptions. What is the assumptions, beta? Please tell me. Assumptions number first, steady flow. Steady flow. That means any parameter with respect to time is equal to 0. What is the second assumptions? Planar flow. Flow, that means any parameter in the z direction is 0. Third one says that fully developed. That means all velocity in fully developed, and fully developed, this says that developed. So fully developed in motion, it is in y direction. So fully developed in y direction, that means dou u x by dou y, dou u y by dou y, dou u z by dou y is equal to 0. That means all the velocity component in that direction is 0. Fourth one, the gravity in a only y direction is equal to minus of g. Yes or no? Y direction, this is your y direction minus of g. Now first we have to apply the continuity equation. Now my dear, this is a fully developed, see, very interesting thing, we can analyze that. This is a fully developed, that means all the layer, it is flowing in the flow of laminar. That means this flow is a laminar. So the flow is a laminar, so the flow, there is no any flow in the x direction. All the flow, it is in y direction. Why? Because let's suppose fully developed, that means fully developed, there is a fully developed. That means if you draw the velocity profile is a linear. Not a linear, but there is a lamina. That means it is in this is the velocity in the form of lamina, in the form of layer by layer, fully developed. That means there is no any velocity in a x direction. There is no any velocity in a x direction. We can assume like that also. That means we have to apply the continuity equation. What is the continuity equation? Dou u x by dou x, dou u y by dou y, dou u z by dou z is equal to 0. Yes or not? This is equal to 0. Now my dear, dou u z by dou z is 0. How? Why? This is the condition number second, planar flow. That means any component of velocity with z direction is 0. And du over dy, it is also 0. Why? Because fully developed. This is a condition number 3. So du over dx, du x direction over dx is equal to 0. Number first term, it is okay. That means ux is a constant, yes or not? Now what is this constant value? This is very important concept I am telling you. What is this constant? Please tell me. What is this constant? 0, 1, 2, 3. So we know that ux is the function of x, y, z and t. Yes or not? Yes or not? Yes. So it is steady, so this is 0. Planar, z direction 0. Okay. Now y, ux, y fully developed, this is 0. This is 0, and there is no flow. That means u is the function of x. Here you can say that, sir, u is the function of x. So u is the function of x, and there is a no flow. That means when there is a flow in y direction, there are two conditions. First one, either there is a turbulency, or second one, either there is a hole in the belt. If there is a hole in the belt, there may be a y direction. That means if there is a penetration in the belt, so there may be a y direction, but there is no any penetration. Also there is a fully developed, so only the flow, it is in y direction, it is not in x direction. That means this is your x direction is also 0. That means ux is equal to 0. That means what is this constant value? 0. So this is from the everywhere. So this is everywhere, either everywhere, in this, that point, that point, that point, that point, that point, in all the direction, this point, everywhere the direction ux is 0. That means what, beta? This is not assumptions, this is your condition number 5. So this condition we have to find. Sir, okay, very good, Rahul. Congratulations to your sister. Congratulations. Very, very congratulations. Which department? Yes. Okay, beta. Very good. Okay. So which department the CSE is there? CSE is which branch, beta? Which subject? Please write the comment. Civil services, which branch? Which subject is there? Yes. Now you have a gate time. Very good. So this ux is 0. This is a condition number 5. So now, my dear, now we have to apply the Navier-Stokes equation in y direction. That why? Because the motion, it is in y direction. Now we have to apply the Navier-Stokes equation in y direction. Okay, please tell me what is the Navier-Stokes equation in y direction? Okay, for the interview, great. So rho y direction, dou u y by dou t plus ux dou u y by dou x plus uy dou u y by dou y plus uz dou u y by dou z. Okay, this is equal to minus dou p over dou y plus mu dou square u y square by dou x square, dou square u y square by dou y square, dou square u y square by dou z square plus rho into g into y. Clear? This is clear? Medical science, great, very good. Medical science, great, beta. I am happy, very. Okay, now, this is the Navier-Stokes equation. This is your Navier-Stokes equation in your y direction, and we know that this is 0. So this is 0 under which condition, beta? First, assumption number first. Why? Because this assumption is steady. Assumption number first is steady. Now, which one is 0? Ux, it is 0. Yes or not? Ux, it is 0. Condition number 5, constant, and this constant is 0. Ux, it is 0, and this is your condition number 5. Now anything, this is 0. Why? Why this is 0? Planar flow, and planar flow is the condition number 2. Okay, and this is your fully developed du over dy, that means y direction velocity is 0, fully developed. This is your third, so this is 0, condition number 3rd. So left side is 0, left side is 0. Now my dear, du over this is 0. Why? Because fully developed 3. This is 0. Why? Because planar, and planar it is the condition number 2. Okay. Now you cannot say this one du over dx, you cannot say. Why? Because it is, this is not 0, you cannot say this is 0. Why? Because here this term is 0. Why? Because ux 0, but you cannot say like that. Okay. And what is zy is minus g. Okay. So now tell me what is dou p over dou y here. This is very important term. That means the pressure variation in y direction. How to check it is 0 or not? That is a very important concept. How to check this is 0 or not? How to check this is 0 or not? For checking of this 0, we have to apply the Navier-Stokes equation in x direction. So Navier-Stokes equation in x direction. Please write down the Navier-Stokes equation in x direction. Rho dou ux by dou t plus ux dou ux by dou x plus uy dou ux by dou y plus uz dou uz over dou ux over dou z is equal to minus dou p over dou x plus mu dou ux square by dou x square dou ux square by dou y square dou ux square by dou z square plus rho into gx. Clear? Now this is 0. Why? Because there is no any gravity force in z direction. Okay. Now there is a steady, so this is also 0. Now ux is 0. Now dou ux by dou y, dou ux by dou fully developed, dou ux by dou ux, that there is no any velocity variation in y direction. Yes or not? See, dou ux by dou y is equal to 0, fully developed, so this is also 0, fully developed. Okay, this is planar, so this is 0. Yeah, you can say that uz is 0, planar, this is planar, so this is 0. Now my dear, now here dou ux, this is planar, this is 0, this is fully developed, this is 0, and there is no any velocity variation. This is why it is 0. Condition number 5, ux is 0. Condition number 5, ux it is 0. So this is also 0. That means, very important, dou p over dou x is equal to 0. That means the pressure in the x direction is constant. That means pressure in x direction is constant. Pressure in x direction is constant. Dou p over dou x is 0. That means p in the x direction is constant. Now my dear, the pressure in the x direction is constant. Let's suppose we have this one. Let's suppose there is a plate, belt is there. Okay, this belt is moving with the velocity u, and there is a free surface. This is your x direction, and this is your y direction. Now tell me, this says that pressure in the x direction is constant. So this is your x direction. So at this point, 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 the pressure is not varying. That means pressure along the x direction is not varying. That means what is this point pressure? P atmospheric. Clear? So at this point also P atmospheric, at this point also P atmospheric, at this point also P atmospheric, at this point also P atmospheric. So here is also P atmospheric. Clear? Clear? Now you have to take, let's suppose there is another cross section. Let's suppose this is x in this direction. So at this point also P atmospheric, at this point also P atmospheric, at this point also P atmospheric, at this point also P. So here is also P atmosphere. So here is also P atmosphere. Now see my dear, in x direction pressure is constant in every cross section x direction. This is x direction, pressure is constant. This is x direction, pressure is constant. So the variation in y direction, the pressure is constant. That means the change in pressure is 0. Y direction also. The pressure in a y direction is also 0. That means hence dou P over dou y is 0 also. Clear? This is the one hurdle point. Clear? That means we have to write here, this is also 0. Clear? This is also 0. So my dear, flow over flat plate, that means any fluid which is flowing over flat plate, the pressure variation in y direction and pressure variation in x direction is constant. Okay, there is no any changes. Okay. Now, so what is the equation now? That means mu dou square u dou u square by dou x square minus rho into g is equal to 0. That means what is the equation now? Hence, what is the equation now? Mu dou square u y by dou square u y by dou x square minus rho into g is equal to 0. Yes or not? See this one. Only this is left and this is left. Other term is 0. Okay. So if you write, that means this mu is constant, that means dou square u y by dou x square is equal to rho g by mu. Yes or not? Yes or not? Now my dear, see here, this is u y is the function of x, y, z and t. X, y, z and t. Now steady, that means this is 0. Planar, that means this is 0. And this is fully developed, that means this is 0. So only is the, and uy is the not a uy velocity in y direction, x, that means x direction velocity is changing. Why? Because at this point there is a no slip condition, there is a velocity and here is the velocity is minimum. Yeah, maybe. So this is not uy is a function of x only. That means uy is a function of x only. So we have to convert this partial derivative into absolute derivative. So we have to take d square uy by dx square is equal to rho g upon mu. Clear? Now, so we have to integrate first. You have to integrate first beta. First integration. This is what is the first integration? Du y by dx is equal to rho g by mu x plus c1. This is first integration. Again you have to integrate uy is equal to rho g by 2 mu x square plus c1x plus c2. Yes or not? So this is your velocity profile. Yes or not? It is clear up to that one? Everyone? This is clear? This is clear, everyone? This is clear, beta? Now we have to find the boundary condition C1 and C2. We have to find the boundary condition C1 and C2. How to find the boundary condition? Pala, number first. No slip boundary condition. Boundary condition. What is the no slip boundary condition? That means at x is equal to 0, at x is equal to 0, what is the velocity u a y? Is your constant capital U. At x is equal to 0, the fluid particles velocity is your u. That means put the value u, this is 0, this is 0, that means C2 is equal to u. First C2 here. Now you have to find C1. How to find C1, please? Okay. Now it's okay, beta? Now sound is okay, please tell me. Now sound is okay, beta, please tell me. Rahul, is there any problem in the sound? Mic it is okay, no problem. Mic it is okay. Okay, 1 second. Mic it is okay. Now it is clear. The sound it is visible. I also watch that video. No, I think your laptop it is a problem. Why? Because beta, in this my mobile there is a Rahul, okay. Okay, Rahul, thank you, beta, thank you, Rahul. Please check that, okay, other one. So C2 is equal to 1. Now how to find C1? This is very important. Anyone please tell me how to find C1? How to find C1? How to find C1 value C1? So C2 is clear. Now how to find C1 constant? That is a very important thing I am telling you. How to find C1, beta? How to find C1, please tell me. How to find C1? Anyone? Continue to the boundary condition. I cross check, no problem. I can cross check, okay, no problem. Now, how to find continuous boundary condition? Yes, very good, Rahul. I am very happy. Continuous boundary condition. That means at this boundary, at the free surface of the boundary, the shear stress at this point and the shear stress at this point is same. Very good. So let's suppose this is our belt. This is our belt and this is our fluid layer which is moving up. Now, so this is your liquid and this is your air. Okay, now? So at this point, this is your liquid and at this point there is a air. So the shear stress at this point and shear stress at this point is 0. That means this is tau of air and this is tau of water is same at this layer. Okay, that means tau of water at x is equal to h is equal to tau of air at x is equal to h. Now my dear, what is the tau? That means mu of liquid dou u, d, only u is a function. So du y direction by dx, x is equal to h is equal to mu of air du y by dx at x is equal to h. Yes or not? Yes or not? Now, Now my dear, what is the next step? Sir, we know that viscosity of the liquid is much greater than the viscosity of air. That means this is very minimum, so you can neglect it. That means you can neglect. Yes, physically how to understand that? See, there is a air, this is your liquid layer, this is your layer of liquid, and let's suppose this is your liquid layer, so liquid layer, and this is your air particle. So air particle in the liquid and the air, there is a very less viscosity, so the liquid will not be able to hold the air particle along with. That means liquid doesn't able to hold the air particle. Why? Because the air particle have a less viscosity, so it will not glide. Yes, what liquid within the water, it will glide, it will move up, but the air have a very low viscosity, it will not glide, so this viscosity is 0. That means here mu of the liquid, and what is the du over dy with respect to x, you have to integrate it. Du over dy, integrate, that means du y over dx, if you integrate it, this is how much beta? Rho g x by mu plus c1. Yes or not? Put the value here, and what is that x? X is equal to h, so this is h. So what is that? Rho g h mu plus c1. So this is your rho g h mu l plus c1, this is your 0. So this is what is the c1? C1 is equal to mu l. Yes, so this is also constant, mu l liquid constant, so this is also constant. So this is your mu l constant, that means this is your minus of, how to write mu, okay, one second, mu g h into c1. So this is your mu l and du over c1. Okay, so c1, it is your rho g divided by mu l into h. This is your c1. It is clear, everyone? Please tell me. This c1 is clear? Second, c1 it is clear? Put this value here. Put the value back. C1 and C2, put the value back. So put the value back. You put the value back, that means uy is equal to rho g 2 mu x square plus c1. Put all this value and rearrange this. This is your 1 by 2 g by kinematic viscosity x square minus g h by kinematic viscosity x plus u. This is your velocity profile. This is your velocity profile. This is your velocity profile. Now, if you find the one doubt, please tell me. Please tell me, beta. Any doubt you can ask. Please tell me. Please tell me your doubt. I am very happy. Please tell me, beta. Please write down. Okay, up to you can write. I will discuss further. So what is uy is that? That means the velocity in y direction. Velocity in y direction is equal to 1 by 2 g by mu x square minus g h by nu x plus u. This is your velocity. Now you have to find the discharge. X is equal to h is not clear. Okay. From here. Okay. Oh, here x is equal, we have to find, this is your h na, this thickness you have h, this thickness is your h, so and this is your x direction, this is your x direction, so we have to find this edge of this fluid layer, this is edge of the fluid layer. So edge of the fluid layer at which position? This edge of the fluid layer at which position? X is equal to h. So at this edge there is air particle, at this edge there is a water particle. So at this, what the distance of this edge from the belt is at h. So we have to take the shear stress at which distance? X is equal to h. And now air particle is also x is equal to h. I hope you are clear. I hope this is clear, okay? I hope you are clear. Now if you find the discharge, so let's suppose this is a belt, this is a belt and this is a fluid, and the velocity is varying, beta. So in this direction, x direction, the velocity is varying. Velocity is vary. X direction, velocity of y is vary. That means, let's suppose this velocity is look like that. I don't know. If you put all this value x1, x2, let's suppose this velocity is look like that. Let's suppose this is a velocity. We don't know exactly, but let's suppose it is look like that. So velocity is varying. Velocity is varying in x direction. Okay, so we have to take a particular cross section of a very thin cross section at a distance x, and the thickness is dx, through which this velocity is uy. Okay, so what is this area? This cross section area is what? Width. This cross section area is what, beta? Dx into width. Width is the perpendicular to the board. So what is the discharge? What is the discharge, beta? Discharge, you know that integration of uy in this area into dA, and you have to integrate uy. This is your uy into area. Area is varying x, so x is equal to 0 to x is equal to h. So integration x is equal to 0, x is equal to h, uy, what is the area? Area is dx into b. We have to find the discharge per unit width in the question. So this is your x is equal to 0, x is equal to h, uy into dx. Now put this uy here, x is equal to 0, x is equal to h, uy put here, 1 by 2 z by nu x square minus gh by nu x plus u into dx. If you solve this one, the value it is minus gh cube divided by 3 nu plus u into h. This is your discharge. Clear? Clear, beta? Everyone please? This is your discharge. Clear, everyone please? Clear, everyone please? Tell me, this is clear or not? So this question is all about this thing. So this is the related to the Navier-Stokes equation, how to apply, but the gate at this level, up to that there is no, they are not asking like that. But what is the catch here? What is the important thing here? Please, my dear, how to apply this Navier-Stokes equation, that is a very important thing. I am telling you, that is a very, very important thing. Only the gate is asking up to this level. This level. That means you have a general 2-dimensional, 1-dimensional velocity profile, it is given, how to pressure gradient, how to that one. This is general things. But you have to try to understand this problem and how to apply the boundary condition, how to develop this table, what is the understanding of this table. Please be careful, okay? 1 minute. What is 1 minute? Okay, this is your 1 minute. Okay. Huh. Okay. So my dear, I will end up here. There is a lots of question is that I will send that free in the Telegram group, the PDF I will send you the Telegram group. So there is a one question of a wind tunnel test. This is very important question, and this is most expected wind tunnel test. And there is a second question, the drag. There is a drag is there, the plate on the drag, there is a triangular plate. So these two questions are most expected question, but the time, due to the time constraint, we are not able to finish this. I will send this problem on that Telegram group with the solution. Okay, okay, Rahul. Everyone, thank you very much to watch this video. And I am again, we have to next subject of the score booster of machine design, and will update very soon on that Telegram group. So don't miss this to join this Telegram group. But I am telling you, you just join this Telegram group so that you are very much aware for all the update. There is free of cost, no any cost is there. So please join this Telegram group, TME/IMS Gate Academy. Okay, please join. All the PDF updates are available. Okay, thank you. Bye bye.